All right, in this module, we're going to start talking about binary eutectic phase diagrams, and we'll continue that in the next module as well. All right, so we've talked about an isomorphous binary system. Here we're going to talk about a binary eutectic system. And the term eutectic is just a term that means low melting point alloy. So we can visualize it in this phase diagram down here. So we have copper and silver, so CuAg. So over here, this is pure copper, and you see that it melts at around 1100 Celsius. And then we have silver over here, which is a slightly lower, it's a little under 1000 Celsius. And yet you see, if we mix the two, they form a liquid at a much lower temperature at around 800 degrees. So we're able to lower the melting point of these two components. It's not somewhere in the middle. It's actually lower than both components. So that's what a binary eutectic system is. It has a very low melting point material. And so you can imagine that these are useful alloys for things like solders, right? Where solders are really low melting point materials used to join two pieces. And so that's what we use them. And this is different than an isomorphous system because an isomorphous had complete solid solubility. Here in the eutectic system, these will develop when the components, in this case copper and silver, have much more limited solubility of the pure components. And so you kind of notice here, excuse me, on the left side, what we call terminal, left terminal, this is alpha. This is the solid that most closely resembles copper. And you see beta, which is the solid most closely resembling silver. However, you see in the middle here, the main part of the diagram, that you see that instead of one solid, there's actually both alpha and beta. So basically what this tells us is that copper and silver don't really like each other. They don't meet Hume-Rothery rules, and therefore they're going to form a mixture and not form a solid solution. So that's what we have with a binary eutectic system. And when we have these types of systems, we often talk about the eutectic reaction because you see here that the lowest melting point is at a specific composition and temperature. We can write a reaction in which a liquid goes straight to two solids. And so this is another way of defining the eutectic system, is because it follows this reaction. So above this temperature here of about 800 degrees, at this composition of 71.9, above it we have liquid, and then if we go straight through this composition and go down, we'll go straight into two solids. And so that's kind of a unique reaction, unique to the eutectic system. And so we can write a reaction. So the liquid at the composition of the eutectic goes to alpha with a composition at the eutectic and beta at the eutectic. So both of those, again, we're dividing the liquid into two solids, and so the compositions are obviously going to be different. And again, we can use our tie line to do that, and we'll see that C alpha E is equal to this point over here, and C beta E is over here, 91.2. So those are our compositions at the tie line, and you can kind of already see the tie lines drawn for us. All right, so that's kind of the basics of this diagram, and we can, like I said, we can fill that out. So the eutectic composition is 71.9, weight percent silver, and then we have 8 and 91.2 respectively as our compositions of alpha and beta respectively. And so this is the reaction that happens upon cooling, and upon heating we would go in the reverse direction. Two solids would become one liquid. All right, so with this binary eutectic system, we also introduce some different terminology for the various boundaries. And so we've talked about the liquidus before. The liquidus is the line that separates some solid to pure liquid above. So there's pure liquid above this line, so this is the liquidus, and the same thing for this line over here. This is also a liquidus. And then we also have a solidus, and this line you see here separates pure solid from some liquid. And you also see that this line over here, right? Pure solid below, and then some liquid over here. So we call this the solidus. So this line, and then this line also would be a solidus. However, we introduce a new line called the solvus. And for this, you think of solubility limit, and this is in fact a measure of that solubility, right? So this curve, you can see, increases with increasing temperature and is effectively the solubility limit of the alpha phase in this alloy. So this is the solvus for this side, and then there's going to be a similar solvus over here, right? So those tell you about the solubility limit. And in this case, if we're talking about copper over here and silver over here, so this is basically the copper phase. So it tells us about how much silver we can add to the copper phase. So there's a maximum amount of 8 weight percent silver in that phase. And then if we think over on this side, this is the silver phase, beta, and it can have a maximum of 8.8% copper before it would form a two-phase, right? So that's exactly the solubility limit that we talked about before. Only in this case, it's solid to two solids. So that's the only limit. So we call that the solvus line. All right, so in this overall diagram, we have 3 single-phase regions. We have a liquid region up here, we have an alpha region over here, and we have a beta region over here. We have limited solubility, right, from these narrow regions of alpha and beta, right, only up to 8 and 8.8%. So there's alpha is mostly copper with a very small amount of silver. Beta is mostly silver with a small amount of copper, depending on your location. The temperature of the eutectic, TE, is this 779 here that you see, this isotherm that we see. And so there can be no liquid below that temperature. And so that's the low melting point that we talked about. And the composition of the eutectic is right here, right? Is right where we have that eutectic reaction that we described before. All right, so now what I want to do is look at some of the different regions of the eutectic phase diagram and show what the microstructures would be of those regions. And so we're going to look at the leftmost side, and we're switching to a lead tin system to show this a little bit better. But this first compositional region is if there is some kind of room temperature solubility limit. So you might not even see this in some diagrams, but this is around 2%, 2 weight percent 10. So basically this compositional range is below this 2 weight percent. And so any of these compositions. And the result of that, if we kind of go through the cooling of this, right, we start with liquid, very uniform, and then we go into this range and we start to form alpha. And then here below it, we form all alpha, right? So it's complete alpha in this region. And when we get down, when we get down to room temperature, it's the same. Everything is the same. So we basically only form alpha if we're in this very narrow compositional range where we're below the room temperature solubility limit. So that's what we kind of expect, alpha. This isn't super common in eutectic systems, but I did want to sort of point this out to you. Let's look at a more practical composition range though. So now we're above any room temperature solubility limit, but we're below the max solubility here at the eutectic. So we're at this composition. So this is our composition now. So this, for this particular diagram, it's between 2 and 18.3 weight percent. So this is the 18.3. So now what we're going to see is we initially see a liquid right up at the high temperature. And then in this region, we precipitate alpha, just like we've seen before. And below that, all of the liquid is gone, so we just have alpha. But here comes the difference between what we just saw. Here, if we keep decreasing the temperature, we see that we fall to the right of the solubility limit, which is this line, right? The solvus. And so what that means is that alpha is going to come down here into the lower temperatures, and this diagram tells us that alpha plus beta should be stable. And so what we're going to see is that we precipitate some form of beta by doing this. So if we go below the solubility or the solvus line, we precipitate out beta because that's the equilibrium set of phases, alpha and beta. So that's what happens in this region of the phase diagram. We have alpha grains, and then we precipitate beta phase particles in this particular region when we go below that temperature. And this is an interesting interesting area of the eutectic phase diagram to look at, because this is useful for something that we've already talked about, and that's precipitation hardening. So we specifically talked about precipitation hardening as a way to strengthen alloys. We form secondary particles in this matrix, right, that we saw, and those secondary particles prevent dislocations from moving, or they impede them. And so this is a region of the eutectic phase diagram in which we can precipitate those particles, because you can think of the matrix phase here, the lighter region, as alpha, and then when we go below the solvus, we form those beta particles. And so those are the darker, other kind of shaped, some of them disc here, shaped particles that we see in this region. And so that's why this particular diagram or portion of the phase diagram is important, particularly for precipitation, hardening, or strengthening of alloys. So again, we had the same kind of reaction that we see here. This is basically the same as what we're seeing over here. And so that's why it's important. And in the next chapter, we're going to talk more about precipitation hardening and how we use this type of phase diagram to get these structures. But I just wanted to sort of preface that a little bit now when we talk about eutectic phase diagrams.